Hi, I'll assume that you watched the previous video. I'll continue from there. In the previous video, we talked about the multitask estimator, and one function that was not implemented there was the get user embedding, which is the subject of our current of the repository and our current learning. So the traditional way, the conventional way of representing a user in a recommender system, both ranking and retrieval, is an embedding lookup table. What it means is, given the user ID, we look them up in a large table, maybe hundreds of millions of entries here, and we use the user ID to hash to a specific location. So for this user ID, every time we will hash to the same location, and we will fetch whatever is in that location of that table, and we'll use that as a user embedding, use that in the model. Based on the backpropagation or the gradient from the model, we will update that same location. And the benefit of this approach is, of course, that you have a lot of specificity in what you're learning about the user. You're giving them their personal space to in your memory to remember about them. And then that also, kind of the strengths are also the shadows, in the sense that if your table isn't very large, then you will have collisions. This you don't have any generalization; it's full-on memorization. There is actually a lot of precedent behind this. If you recall the collaborative filtering approach or the latent factor models, they would represent a user-item interaction by what they need, by the representation of the user, it's the user embedding, and the representation of the item. The prototypical implementation of collaborative filtering can just be done with two embedding tables, one for the user ID space and one for the item ID space. You look at the user, look at the table, plug the user embedding. Look at the item, look at the item ID table, plug the item ID, item embedding, and then if it's a dot product based system, then like a retrieval two-term model, then you take dot products. Otherwise, if it's an MLP, then you just feed them into your MLP and learn using backprop. But the point here is that this embedding lookup table is steeped in successful recommender system literature like collaborative filtering. Okay, so we have this function, unimplemented function, get user embedding, and we will look at the first implementation of it, the user ID lookup representation, and after initialization of superclass, we set up an embedding layer and an embedding, which is the given hash size and of the dimension that you're looking for. And in your get user embedding, you just look up an embedding basically hashes the input, the user ID, and goes to the whichever index the hash value is, and finds the embedding from it. Okay, so in this approach, we used a lookup table approach, where for each user ID, we hash to a certain location and use the embedding. Okay. Now, another approach that people have done, and there's this very nice paper called Deep Hash Embeddings from Google. What they do is it's quite magical, but it seems to work, produce similar results. So in this approach, the user ID was mapping to a specific location in a large table, but here there is no table. They take the user ID, and I have a deterministic hash function. That means the output of this hash function will not change no matter what the user does. Like, if user watches, let's say I'm making a movie recommender system. Either watches horror movies or I don't know, action movies or whatever they do, the output of this hash function will not change. It's a deterministic hash function. But what happens after that? This is the part that actually changes based on backpropagation. So they take this, the output of this hash function is, let's say 256 dimensional vector tensor. Then they pass it through multiple layers. I believe in the paper, deep hash embeddings, I think they had used 3 or 4 layers, but here I think it's probably important to have quite a few layers. And these are normal, hidden layers, like with everything fully connected and activation functions, etc. And seemingly, just by backprop, this stack of hidden layers was able to memorize, but also generalize. And finally, the performance was very similar to the large embedding table approach. So the memory requirement here is, let's say you have 2 billion users, and this, let's say, dimension is 100 or something. Then this requires 200 billion floating points, right? And this, the memory requirement here, the number of parameters here is much less. Let's just say this is 256 and 256 and 256. So you're talking maybe 4 times 256 cross 256. Yeah. So Deep Hash Embedding is a great paper. I recommend you to read them. My focus here is not to spend a lot of time on DHE, but to learn from that. And then we will use this approach to generalization in our approach. So what they did was they took user ID, hashed it, deterministically hashed it to output, then passed it through a set of layers and used it in the model. Okay, and you can see the general implementation, although I've not really implemented the hash function properly, but here you see the stack here, and you see a dummy hash function. This is not correct because this will give you a different value every time, but you can fix this later. This is more to give you an idea of what happens. Eventually, in our implementation, we will not need a hash function. And the get user embedding calls this deterministic hash and then passes it through an MLP stack. By the way, before I move on, you can look at some of the test files to understand how to use them. So I think so far we have talked about the user ID lookup, and this is how we, like, the sort of inputs that we have used here will help you understand what we're doing.